we will review electric potential. In Chinese, potential is called 电位. So first, electric potential is equal to electric potential energy divided by charge, and charge is Q. So electric potential is V, so it's PE divided by Q. In terms of units, V's unit is volts, and PE is joule, and Q is coulomb. You can also write it like that. 2, a positive charge, so you can look at this graph right there. And naturally, it will move from high to low V. So this side is positive, so that's high V always. This side is negative, so that's the low V. So for positive charge, if you put it right there, since negative attract positive, so it will always go to the right. For negative charge, you want to put it on this side, on the right side here. Then it will move from the low V to the high V. Okay? And for either for positive or negative charge, they always go from high potential energy to low potential energy. So I repeat, okay? Positive charge will naturally move from high to low potential. Negative will move from low to high potential. For both positive and negative charge, they always move from high potential energy to low potential energy. So for example, this side here is positive charge. You have positive charge here. So at this position, the potential energy for this positive charge is high. And when it goes to here, the potential energy for this charge is low. So it's go from high to low. But for the negative charge, so negative charge is here. And for negative charge at this position, the potential energy is high. Potential energy, not potential. Potential is low, but potential energy is high. So it naturally go to the left, and will go from high potential energy to low potential energy. I hope that's clear. So now we're going to talk about energy conservation from 1 to 2 for positive charge. You can do it similarly for the negative. So from positive charge, go from high to low V. So from 1 to 2. So positive charge from 1 to 2. PE is converted to KE. So if you just let it go, then when it comes here, it would have velocity and it would have higher kinetic energy. And here you started with V equal to 0. So velocity equal to 0 here. So you can write it as PE1 or KE1. So KE1 is 0 because velocity is 0. So you hold it there, and then you let go with your hand. Then it goes over here. So you have KE1 plus PE1. So PE1 is not 0, it's higher, and it will be equal to KE2, which will have velocity. So it's not going to be 0. This is not 0. But PE2, we're going to assume is 0 at this low position here. So then we'll have PE initial is completely converted to the KE final. All right? So this is the energy conservation. Energy conservation. 能量守恒 conservation. And this energy here is PE, so potential energy, and the KE. So you're looking at those two. Okay, so number 5, we're looking at the work now, right? So we're going to move from 2 to 1. So if you want to do work by external force, right? We're looking at external force, and this is F. This is the external force right there. So if you want to go, so velocity is 0 here, you're going to move it over, then because this one is repulsive and this one is attractive, so you need to apply an F, and the F has to be equal to E times Q. So this external force is equal to, the work done by this external force F is equal to this F times the distance D. So that's W equal to FD, and that's going to increase the potential energy of this charge. So 1 is higher potential energy, and 2 is lower. That's equal to delta KE. And so the delta KE is equal to PE1, which is final, minus PE2, which is initial. And by definition, since V is equal to PE divided by Q, so we're going to put that into here. So PE is equal to V times Q. So we're going to say PE1 is V1Q, PE2 is V2Q. So then V1 minus V2, we can write that as V12, okay? And V12, I'm just going to assume we're going to use a simple notation called V. So call that V times Q. All right? So you're going to put the VQ over to this side here. And then right here, the F, I'm going to substitute EQ in there. So then FD will become EQD. And then this VQ will come over there. Then the Q cancel out. Then you will have V, right? So Q cancel out. So then V will equal to ED now. So that's a good formula to know, to use in the two parallel plate. This is for the two parallel plate. 两个平行的金属片 two parallel plates situation. So the unit is volt for V, and E is Newton divided by Coulomb, and D is meter. So that's your unit right there. So we're going to continue. Review the breakdown voltage for air. So air usually is an insulator, 绝缘体. The voltage such that the air will become ionized, so 离子化, ionized 离子化. So when it ionized, then it can conduct. So conduct means 导电. So when the voltage keep increasing such that air itself is no longer an insulator, it becomes a conductor. That's called a breakdown voltage for the air, or for any other material. So V is equal to ED in this kind of parallel plate situation. When the V increase, then the E will increase. At some point, this electric field will be large enough so that the air will become ionized. Number 7, equipotential line. So meaning the same V. Equip is same. Potential means V. So same V line. It's always 90 degrees to the electric field lines. I'm not talking about electric field. I'm talking about electric field line. So 电场线. Okay, electric field line. Okay, so electric potential line means V is the same at all points on any particular line. So for example, you have two parallel plates. These orange lines are the equal potential lines. Sometimes they also call it ISO line. ISO means same. ISO line, right? So ISO is like isothermal, isovolumetric, right? The ISO, same line, okay? So same something line. So they call it ISO line sometimes. So for example, for this curve here, right? Because near the edge, it will curve. So this one is 10 volts. And then right here will be 9 volts. And then right here will be 1 volt. And right here near the terminal will be 0 volts. So those are called equipotential lines. And for like a single charge, then this orange, it's an equipotential line. And this one is also equipotential line. So you can have more, you can draw more to it. So now if you look at one of the line, for example, the inner circle right here, 1, 2, 3. So that one there, V1, so V at point 1, V at point 2, they all equal to 100 volt, for example, right? So this is just an example. And then as you move away from this charge, it will become lower potential. So this one here is 50 volts, for example. So then we know at 1 prime, 2 prime, 3 prime, and then continue this path here along the circumference. All of them has the 50 volts. Yeah? Okay? So now you can see the electric potential is decreasing when you go in this way, right? So V is decreasing, V decreasing as you move this way. But V is constant along the circumference. 所以电位是一样的，在这个圆周上。好，那在这个圆周上，电位也是一样的。All right? So, and this black line is the electric field line, right? I'm not talking about electric field. I'm talking about electric field line, right? Electric field will be, let me change the color here. Electric field will be, so will be like that, right? And then it will become smaller, right? And then it will become smaller. Those are called electric field. But the electric field line just, it connect this electric field and then make it electric field line. All right, so we're going to continue reviewing. Number 8, EV. V is a capital V, electron volt. So together, this is the energy units. It's for a small world. So when we go into the atom and inside the atom, we're usually using EV. So it's the energy gained by an elementary charge. So a particle with an elementary charge through a 1V potential difference. So for example, if I let go a proton, which has a elementary charge, just like electron, and it's positive. So if I let go, initially at rest at position 1, and it's going to arrive at position 2 with velocity. So you have kinetic energy. So at position 1, you have 0 kinetic energy. So the kinetic energy difference between 2 and 1 is going to be just the 2 because Ke1 is 0. And that will be equal to 1 EV since I have the voltage is 1 volt on the left side and the 0 volt on the right side. So that's going to be equal to PE1 minus PE2 using the energy conservation. So then by definition, that's V1 minus V2 times Q, because electric energy is the electric potential times charge, or electric potential is energy per charge. So then this V1 minus V2 is equal to 1 minus 0, which is 1 volt, and Q is 1.6 times 10 to the negative 19 coulomb, which is electrons' elementary charge. So then this is equal to 1 volt times electron. So that becomes 1 EV. So that is what that is. So 1 EV is exactly equal to 1.6 times 10 to the negative 19 joule, right? So this is equal to 1.6 times 10 to the negative 19 joule, according to here. So number 9, V, so electric potential is a scalar, unlike E, electric field, which is a vector. So when you handle E, you have to handle it like a vector. When you handle V, you have to handle it like a scalar. And this V has the Q that's using Q in there. This Q, you must using the sign correctly. So if you have a negative charge, you have to using minus. If you have positive charge, you must using plus. So V due to point charges like Q. So let's say if you have a Q right there, and then surrounding this Q at a point distance of R, that has no direction, but there's a V right there. You don't need an additional charge. You just need this Q charge. And at the space surrounding Q will have this electric potential. And that's equal to KQ divided by R. All right, so just note that V and E exist for space around a single charge. So you don't need 2 charges. But P and the electric force, you need to have 2 charges in order to have the concept of PE and the F, right? Remember, PE, it's for 2 charges is equal to K Q1, Q2 divided by R, right? So 2 charges, right? F is equal to K Q1, Q2 according to Coulomb's law, divided by R squared. Again, Q1, Q2, right? But V, you just need a Q and also E. Okay, so in this case, this KQ divided by R, if this one is positive, then V1 at the point 1 will be positive because Q is positive. At 2, V2 also positive. But since R is bigger for 2 and is in the denominator, so V2 will be smaller than V1. Okay, all right, almost there. 10, capacitance. Capacitance in Chinese is 电容. So as a symbol, you will write them like that. They are equal size, all like this, okay? And if you draw like that, and that's positive, negative, this is a battery. That's a battery, a DC battery. In Chinese, 电池, right? Okay, so by definition, this capacitance is equal to epsilon 0, which is permittivity of free space. And that's equal to 9 times 10 to the negative 12, and that's a unit. So A divided by D, and this A is the surface area. So look at this graph right there. The A is the surface of this. It's also the surface of that. So you don't use 2A, you use A. And this is Q, positive, and this one's negative Q on this side. So anyway, the C has nothing to do with anything else except epsilon 0. So the space. So whatever space you have, and then A, the A, and then the distance. So it's very geometric, right? It's very geometric. All right. And then also the Q that you have will have to do with the voltage that you attach to them. So let's say if you attach to a V right there, you connect this and you're starting to charging them, then the Q that you will actually getting, negatives here, the Q that you're getting will be the C that you have times the V, the external voltage that you apply to it. And that will be your Q. And of course, this is C in units, Coulomb, and this C is in farad, and the V is in volts. So these are in units. Okay. So, and now if we don't want to have free space, instead we put an dielectric material in the middle like that. So it can be a paper or some kind of plastic. You put it in there. Once you put it in there, the formula will become K epsilon 0. So this K is a dielectric constant, and K is equal to epsilon divided by epsilon 0. So it's a ratio, and epsilon, right, will be larger than the epsilon 0 for something that's not air. So then this number is usually larger than 1. Okay. So now you can see the C will increase. When C increase, you'll find out that the E will decrease because you have, this is polar. You see that? This is negative, positive. So then the electric field that's introduced is going this way, but original electric field is going this way, right? So then you end up with a smaller electric field in the middle, all right? Okay, so last topic is going to be electric potential energy for a capacitance. So PE for capacitance. So that's equal to 1/2 Q times V. So why is that? So you have the Q, the charge that you will get to in the end, and you have external volt, right? External voltage. So as you started to charge, this Q will increase from 0. So it's going to start increasing as V keeping constant there. And then by the time you saturate it, then you will have this area here. This area is in D. This area is equal to your potential energy that's stored inside the capacitor. So this is equal to 1/2 according to the triangle. This one here, let's say it's V, and this one here is Q. Okay, so then you have Q times V. And then we can also using the formula of Q equal to CV. So Q is equal to CV and times V. So then you can have 1/2 CV squared, which is very similar to our spring potential energy. And that's equal to 1/2 And then instead of C, you have K, spring constant. Instead of V, you have the displacement of the spring squared. Okay, so that is the spring potential energy, but that's the capacitance. But both of them are used as energy storage unit. So in Chinese means 储藏能量, energy storage. Right? 储藏能量, 储藏能量. Okay, so that's all we have. Keep watching and keep learning. And go ahead and subscribe. Bye-bye.